Astrophysics at Pune during 2004-2006 and worked as a DST woman scientist in Osmania University during 2006-2009. She taught at the Mufakam College of Engineering and Technology, Hydrabad during 2010-2015 and joined Maulana Azad National Urdu University, Hyderabad in 2015. So with this very brief introduction, I invite Dr. Priya Hassan to deliver the lecture. Thank you.
Thank you so much for that. I think there's an echo somewhere. Maybe somebody's mic. Okay, now it's fine, right? Okay, sir. So thank you so much. Thank you very much, sir, for inviting me. And it's a pleasure for me to be talking over here with this very good audience that you have over here. And I'm very happy to be sharing my my thoughts with you. So I'll first present my screen. And I hope you can see my screen properly. Can you see it? Hello, sir.
Yes, madam. It is visible, madam.
You can see it in full screen mode, right?
Okay, madam.
Okay, sir. I think we'll have to get your... Yes, sir.
Madam, your mode is not in full screen, madam.
Okay, 1 minute. Let me try again. Get it again. Is it now there or no?
It is sharing, madam.
It is fine in full screen mode?
Yes, madam.
Okay, thank you, sir. So hello everyone, and I'll be today talking to you about career pathways to astronomy education and research. And I work at Maulana Azad University. So I think somebody's mic needs to... Okay.
Madam, not in full screen mode, madam.
Okay.
The screen is not in full screen mode.
Okay. Let me. I should.
So, ma'am, I think when you're sharing the screen, you may have to do the full screen first, and then maybe click on the share.
Okay. I'll try doing that. Okay. I'll take it. Okay, you're saying to entire screen.
Yeah, and then select only the full screen one and not the presentation one.
Yeah. Okay. So I'll take the. So play from start. I do that one only, no? The normal one.
Yes, but I don't think. Oh, yeah, we see it now.
Okay.
It's fine. Thank you. Yeah. So like I mentioned, my email is here. So even after this talk, if you have any questions or queries, you can always write to me, and I'd be happy to answer your questions. So what am I going to be talking about today? So first, I would be talking about the importance of astronomy. Why is astronomy so important and so strongly related to our lives, right? Next, I will talk a little bit about what do astronomers study, and then what facilities, telescopes do we have in India, the Indian space program, and how could you plan a career in astronomy based on these ideas, right? So, now career choices are life choices, and since most of you all are teachers, I'm sure a lot of your students would be looking up to you for advice on how do they need to plan their careers. And that is a very important question. I keep telling students that it's a very important thing to, take some time to decide what is the career you want to do and how do you want to plan it, right? So students actually need to give a good amount of thought and a good amount of introspection into themselves, into, assessing what is it that they actually like, what keeps them happy, what keeps them interested, because finally your career is something which you're going to do for the most of your life, right? And it is a good thing, obviously, if it is something that you enjoy doing, something you like doing, then that would be the right career choice, because being in the wrong career could be something really very, would make a person very unhappy. So, so I talk about my career choice, and with an idea that that can help other people to plan their careers. And many of us, when we look up at the stars in the sky, right, we often wonder whether there's life beyond our planet, whether there are more stars. Is our planet the only one where there is life, or what is the origin of this universe? What all has happened, right? And how did it all start, right? Where did this universe start from? What was it all about? Now, the method of science is standard, in which we actually look for patterns. And in patterns, we look for patterns in space, like what I show you in these images over here. These are patterns in space where you can see a certain design getting repeated, right? So a repetitive pattern, right, where there's a repetition either in space or in time. And that's what we actually call a pattern, when you have a repetition in space or time. And then we try to look for some kind of an understanding as to why do we have this kind of a pattern in space or time, right? So the first simplest pattern which we all see, there is the thing about day and night, right? And that is the simplest thing which one can observe, and that's again a pattern. It's a pattern in time. And you also, if one observes, you see the sun rising in a certain direction which we call the east, it sets in another direction which we call west, and the day-night separation is approximately 12 hours, right? So this is what people observe. It's a clear pattern. Now the idea is one has to give some kind of an explanation or understanding as to why do we actually have this pattern. And why do we have this pattern? So it was explained with the sun rising and the sun setting. That was the simplest picture, where you think of the earth as a stationary object and you have the sun rising and setting, which actually is what you're observing. But this very thing, right, could be used to understand things much better. Like what you see over here this is called a sundial, right? So we know that in the morning the sun rises, it reaches up the zenith at 12 o'clock and then sets, right? And therefore, one of the simplest application of this knowledge was to actually use this to find the time. And how do you find the time? What you see down over here is a very primitive kind of a clock, right? Where you can actually see that as the sun rises or sets, you can actually put, in this case you have stones with numbers in there, which are actually showing you how does this change with time, right? So you have the shadow coming at various locations, right? And this could be actually used for timing. And such a timer is called a sundial, because this is basically using the motion of the sun to actually measure the time. And this is, something, if you are stranded on an island or something like that, this is exactly what you're going to use to find out the time. So if you're stranded on an island, or you're stuck somewhere, the simplest way is just look at the shadows, right? Or you needn't even be stuck somewhere on a normal day. If you today go out in the sun and you look at the direction of the shadow in the morning before 12 o'clock, then obviously since the sun rises in the east, your shadow will come in the west. So your shadow is showing you the direction of the west, and the opposite side is the east. So based on that, you can directly define your cardinal points. In the sense, you will directly know where is your north, south, east, west. So just based on this simple understanding, you will know your cardinal points and you can actually find out your directions, right? So this is something which we've been even training forest officers that, how could they actually use the stars or the sun in that case to actually find their way out in the forest if they are lost, right? Supposing, you'd say in today's times we have GPS and you have smartphones, but you could always have a case where, for example, your smartphone is drained out, there's no more battery in it, and hello, is the audio video fine? Is everything's fine?
Yes, ma'am.
Okay, sir. Yeah, because I had some message. Okay. So in short, what happens is this very information can tell you your cardinal points. So we all actually use it for forest officers to guide them that if they are lost in the forest and assuming that their smartphone is, run out of battery, then in that case they can directly find their cardinal points just by seeing their shadow in the day. Right? In the night there's another way, I'll show you that. but in the day they can directly get their cardinal points by seeing the direction of the shadow, and they can find their way back home, right? So just a simple observation of day and night can actually work as a clock. It can actually work as a, for cardinal points to tell you north, south, east, west, and it can be used very effectively. Now the next pattern which we see is the pattern of seasons, right? The pattern of summer, winter, which we have over here, the 4 seasons, famous painting, and here you know that there's a difference in the temperatures, right? And this was again explained by the position of the earth while it goes around the sun, right? And what is the most important factor in this case is the tilt of the axis, right? The tilt of the axis is what actually causes the seasons. Many people have a misconception that because the earth has an elliptical orbit, right? So summer is the time when, when the sun is closer, and winter is the time when the sun is further. But that's exactly the opposite. That's absolutely not the case. You will actually see that the perihelion, or the time when the earth is closer to the sun, is actually in January. So in January, actually, the earth is closer to the sun than it is in summer. But the seasons are basically because of the tilt of the axis and not because of this difference in distance, right? And therefore, based on how do you apply the understanding of seasons? That is basically applied to all agriculture, right? So typically, India being an agricultural country, one needs to know when to sow seeds, when to have the harvest, when to, it's all agriculture related, which is obviously related to the sun in the sense when will it be hot, when will it rain, when will it be cold, and that will define which crop is going to be put at which season, etc. And therefore, for Indian culture or Indian this thing, we have it very important with the relation with agriculture. And based on that, we have all the festivals which are defined. They are all based on agriculture, right? Based on the seasons, because we need to know when is the commencement of summer. For example, once Holi comes, we know it's going to be summer, and then it's going to get warmer, right? Similarly, we know exactly when is whatever season, whatever this thing is defined by the festivals. So the festivals are times of actually marking these events, right? Beginning of summer, beginning of winter, end of summer, etc., right? Or coming of rains, etc. And based on this, we actually have the application in the form of calendars, right? So the motion of the sun going around the earth is recorded in the form of calendars. And calendar is basically a system of organizing dates. You give names to periods of time, days, weeks, months, years, etc. And they can be, again, the calendar is synchronized with periodic things, right? So the simplest periodic phenomena which you can actually see is the phenomena of the moon phases, right? You see that the moon has phases. You go from crescent moon to full moon. And that is the basis of the Islamic calendar, right? Where you're basically monitoring the phases of the moon, which are very easily observable. And therefore, from new moon to new moon, you can count a month. And in that way, you can do it. But the one problem with the lunar calendar is that it does not synchronize with the seasons, because the seasons go with the sun, right? And therefore, most of you will be aware that, for example, Islamic festivals, for example, Ramzan, there are times when it comes in summer, there are times it comes in winter. So it's not exactly related to seasons. And therefore, the other calendar is the solar calendar. The solar calendar, for example, the Persian calendar, is a one which goes based on the sun. Or let's come to the Hindu calendar, that is lunisolar. So it is a combination of luni as well as solar. So what happens is to adjust the extra days, because 28, right, a 20-day cycle of the moon does not fit into 365 days. So it is not a multiple of 28. And therefore you have an extra month which is added to the Hindu calendar to synchronize it with the seasons. And therefore you'll see that Hindu festivals fall along with the seasons, because they are basically to do with agriculture and they have to be synced with agriculture. And therefore what we see is festivals, like I mentioned earlier, they are markers of important astronomical events. So therefore on important astronomical events, you have a festival, right? And this would apply to lunar as well as solar calendars. There are festivals which are the marking of the new moon or the full moon, etc. And based on that, you can have calendars, right? The other important motion we see in the sky is you see the motion of stars and planets. Now, planets have a slightly zigzaggy kind of motion. So here you can see this is the motion of a planet, where you can see it moves forward, backwards, and then forwards. It also can loop. So this is what is called prograde motion, retrograde motion, prograde. It kind of loops, right? They don't have a very straightforward motion compared to stars. If you stand in the night and look at stars, see the way they rise and set, you will see them rising and setting like this, right? In a fixed manner where they rise, like the sun, exactly like the sun. But in the case of planets, you can have this kind of a loopy movement. And that's why planets were so-called named planets, because a planet means a wanderer. So a wanderer does not have a fixed direction of motion. It kind of loops around. So based on that, we define planets in this thing. And based on that, you had the simplest model in astronomy, which was called the geocentric model, which was supported by Aristotle and Ptolemy, where it said that the Earth is the center, and the sun and the sun and the stars, everything goes around the Earth, right? So that is what was called the geocentric model, which was the model which was prevalent for many, many years, because it actually fit with what we observed, right? We thought the Earth is stationary, and the sun and the stars, they all seem to go around us, and it kind of fit with what we observed, right? And that's why the geocentric model was very successful for many, many years. Now, later on, this model got changed with a model which is called the heliocentric model. Now, the heliocentric model was the one which was put by Copernicus, and this was again based on observations. One was the observation of what I told you, the planets doing this loopy motion, right? They come ahead, they come behind, they loop like this. So in geocentric model, you can see that the planets loop like this, right? They go backward, forward, things like that. And the other thing is, it was observed that planets, for example, Venus, these are images not of the moon, this is of Venus. So if you actually see Venus through not a very large telescope also, even a 2-inch telescope, you will see that Venus actually shows phases, like the moon. And to explain these phases as well as this loopy motion of planets, Copernicus, this is Galileo, who actually observed the phases of Venus with his telescope. Here you have Copernicus. So Copernicus gave a very simple explanation to explain why do these planets actually have this loopy kind of motion, right? Which was not understandable. So therefore, what Copernicus did is he applied a principle in science which we call Occam's razor. Occam's razor says that if you have two explanations for the same set of evidence, then you actually take the explanation which is the simplest, which has the fewest assumptions. Okay. Now with geocentric model, since you had to have all these planets looping around, coming forward, coming backward, it was very difficult to explain why do these planets do this kind of a motion, right? Or why does Venus, for example, have phases, right? And Copernicus realized that if you put the heliocentric model, where you put the sun in the center and you put Venus in an orbit inside the orbit of the Earth and all the other planets outside, then in that case, you will actually you can explain the phases of Venus as well as you can explain the loopy motion of planets. So what happens is when the Earth is going around here, this planet, for example, at some point could be moving ahead of it, and then when the Earth comes this side, it could be moving behind it, right? So as Earth goes around, these planets, the outer planets, will move forward, backward, depending upon this thing. Similarly, even with Mercury, Venus, and Mercury is too close to the sun to show phases, but Venus can show phases depending upon what is the angle between the Earth, Sun, and Venus, right? So, so that was a very important application or understanding of the heliocentric model, which was given by Copernicus. So by then, people realized that it is actually the Earth going around the sun and not vice versa, and that is how we can explain it. Now, people also realized, like when I showed you the picture of how do stars move, stars rise from a place and set. You realize that there's a point over here in the sky which does not seem to move. And that is what we call the point of the pole star. Okay. And that was realized to be the axis of rotation of the Earth, because that is why that point does not move. And so what was realized is that in a typical night, what you see is all the stars go round, but the pole star or the North Star does not move. And it is realized, obviously, that the pole star, since it shows the pole, it actually shows the latitude of a place. So I will show that to you over here. I had an animation for it. Oh no, it's not there. Okay. So what was realized is that you have these stars, and as they go around the pole star, you can actually define the pole star, and the height of the pole star will give you the latitude of your place. So if you look at this diagram, you can see the elevation of the pole star, and if the elevation angle is 50 degrees, that shows you the latitude. Now this was something which was very much used, especially for all these countries which had the seafaring nations, essentially European countries, which were pre-colonial times. They had to be conquering the oceans, right? And if you're out in the ocean, it is very important to look out at stars so that you can define your directions, right, or your position. And therefore, essentially all sailors, they all knew how to identify position using stars, because the stars were visible from the sea, and from the sea they couldn't observe anything else, so they had to use this to be doing it. You could not do the thing which I told you about shadows, because the sea, the ship is rocking, right, and therefore the ship rocks, and you cannot define your shadow is not going to be stationary, so you can't use the earlier method I showed you for cardinal points. You have to use the stars, and therefore they use the pole star to actually get the latitude of the place. The next important problem was the problem of the longitude. How do you actually define your longitudes? And therefore what you can see over here is the prime nations. For example, Britain, and this is France. So Britain had their Royal Greenwich Observatory, which defined what is called the prime meridian. This is the line at which you have 0 longitude, and they defined this prime meridian, and based on this you could define longitudes. Similarly, Paris Observatory was set up by the French to again solve the longitude problem, and in this way longitudes could be defined. So you, at that time, progress for a country, the scientific progress, right, was obviously defined upon how they could navigate the seas. So if you see that at that time, building ships or knowing how to navigate through seas was something very important for the progress of a country, which also included navigating the skies. And therefore all these countries, they had almanacs, ephemeris, where they actually would note the position of stars so that they could actually find out their position. So they defined methods of actually finding their position in the sea. I won't go into those details, but essentially it was using astronomy. So sailors also had to be very good with their skills in astronomy so that they could define their position in the sea. And then comes up astrology, right? What was astrology? Astrology was linking of the stars to your fate, right? And but we have to be very careful in that, because astronomy is a study of the universe and the contents outside the Earth's atmosphere, studying the celestial bodies. But astrology has this, there is no logic. It actually links these things to your life and your destiny. And people actually started believing, even to this day, in astrology, where you actually think that this will actually define your fate. So astrology is often called even, it is called the stepdaughter of astronomy, because essentially in astrology there's no science at all. You are using the science of astronomy to give you illogical definitions, right? So that got up this thing of astrology, but astrology played a very important role in astronomy because it led to the development of Fajr astronomy, because all kings needed an astrologer who could tell them what should they be doing, how should they be planning their, their events and things like that. We'll move a little ahead of how exactly astronomy has affected our lives, and we can actually see that if you actually even see in photography, imaging, Kodak is the big company which actually made films to take photographs, and Kodak actually was originally created so that solar astronomers could record the changes in the surface structure of the sun. Okay, And that's when Kodak started developing the film. And that's when people realized that that could be used for various other purposes. For example, in medical and industrial purposes, for artists, for for various things. So the whole application of photography, which started off with the study of the sun, then got built on to all other branches. And then the thing which we are so used to using, digital cameras, which all of you all have on your phones and your laptops, etc. It was actually developed again for the case of astronomy. So you actually had charge coupled devices, right? And this is basically, it was developed for the Hubble Space Telescope. For the Hubble Space Telescope, they needed to have digital cameras so that photons could be easily detected. And that's when charge coupled devices and digital cameras were originally developed for the Hubble Space Telescope. And then it was realized that these digital cameras could be used for so many more things. And now it's actually difficult to even chalk out how many things do we actually use digital cameras for. Not just our personal cameras, webcams, mobile phones, but everything has moved to digital imaging, right? In the aerospace sector, right, like I mentioned, you had imaging, image processing, image processing is something which we do a lot in astronomy because we have images and we have different ways of processing those images to get information from it. Defense satellites, right, they are essentially telescopes which are pointed towards the Earth to give you, further information. You have observations of stars, models of stellar atmospheres. They also, various other things which were applied in aerospace industry, which actually came from astronomy. To the energy sector also, you'd be happy to, this thing to know that all their lithium batteries, which you're actually using on your cell phones or your laptops, etc., all these were also developed basically for astronomy, okay? And again, for the space telescopes, etc. And they were developed for that. Similarly, technology to image X-rays was actually done for X-ray telescopes, which is now being used for medical imaging as well as other factors. Even in medicine, astronomy has contributed a lot to our lives. So, for example, because you are trying to get images of objects which are obscured, right, because of the body, and again you need high resolution images, and therefore various techniques which are actually used in medicine. For example, CAT scanning, MRI, PET, etc. All these are technologies which were essentially developed for astronomy. Similarly, programming languages, clean working areas, etc. These are all from astronomy. There's a lot which has happened in even military and law enforcement with camcorders and electromagnetic interference. All these things have this thing. Faster travel, right? Because technology was developed for space shuttles and even rumble strips which you have on the roads. These are ones which actually came in because of space technology. So what we see in smart lives, in our today's daily lives, what we see is our smartphones. The GPS in smartphones is thanks to astronomy. The battery you have is again thanks to astronomy. The digital camera which you're using is essentially because of astronomy. And this therefore gets applied to, like I said, the GPS thing, which you can use for your Google Maps, for various things, as well as celestial navigation, right? Where earlier, where you had sailors who had to study astronomy to know how to navigate in the sea, but now you can actually navigate using so many other methods. Some things which you would not even know, that even memory foam, right, which is there in the mattresses, was essentially done for space shuttle crashes. So they actually developed that kind of thing. Now it's all in household items, so we do not even realize it. As well as astronomy has contributed very strongly to climate study in the sense of tracking weather patterns and storms, etc. So what we actually see is astronomy has been a part of human life since a very long time, right? So we saw that from our festivals to the functioning of agriculture, as well as navigation, as well as so much effect in our day-to-day lives. A lot of it has come from astronomy, right? So I will move ahead, or are there any questions which people want to ask, or I can move ahead to what do astronomers study? Right. Okay, so I'll move ahead. If you have questions, you're most welcome to ask. So what do astronomers study?
Madam,
Yes, sir.
madam, good afternoon. Madam, I came late actually.
Yes.
Just joined 20 minutes back. I have a small question.
Yes, sir.
Regarding astrology and astronomy, I have a little bit doubt because astrology they are doing some little bit mathematical calculations involved.
Yes.
Ma'am. Lot
Yes,
of
sir.
maths involved. They predict something. Sometimes it becomes coincidence also, ma'am. Is it
Yes.
real calculations? That's what I'm asking. That astronomy and astrology, you are differentiated properly. I agree, ma'am. But that
Yes.
maths calculations and all something they are doing, still they are doing some lot of arithmetic calculations. Right?
Yes, yes, yes. So, the calculations they are doing is fine. That is right. I mean, yeah, it depends on whom are you referring to, but essentially those calculations are done fine, right? You can actually use your calculations to say what will be the position of Jupiter in the sky tonight, right? Where will Jupiter be today, or where is Saturn today, etc. So, correct. They are using calculations. That is right.
Yes, ma'am.
Because you can verify it also by going and looking up in the sky. They say, oh, Jupiter is there, or Saturn is there, or Mercury is there. That's all fine. The problem comes in the correlation. If I tell you that Jupiter is in the sky, that means today you are going to fall sick because Jupiter is in the sky, or because Mercury is in the sky, and hence you are going to get married next month, right? So
yes,
that thing, there is no logic in it, right? If Venus is in the sky and I tell you, oh, that means I'm going to get married next month, that is obviously no logic. So that's why astrology is called the stepdaughter, because it is using the information of astronomy. It is using the information. I can use the information to tell you today sunrise is going to happen at 6:15 in the morning, right? But then if I tell you that you should get up before 6:15, because if you get up after 6:15, then you will not, then you will, supposing if you are, giving some, writing some thing, or you've got to do something, okay, getting married, for example, again, another example.
Yes.
And if I tell you now, if you get married before the sun rises, then it will all be good. If you marry afterwards, it will go bad. Then there is no logic. So that's the problem. So astrology is using calculations. That is all correct. But it is misusing it in the sense that logic is crazy, right? That we know that if you have twins, two children born at the same time, everything is same in the sky. But most of us, if you know any twins, even in your family, you know that both of them have very different lives, right? They are in, different professions. One could be happier, sad. I mean, everything could be very different for both their lives. And if it was astrology, then it should have been exactly the same, because the planets, everything was at the same position when they were born, right? So astrology is in a way misuses the astronomy information. But like I said, that generally, if you want funding an astronomer, I want you to pay me so that I look at the phases of the moon, right? Who is going to pay me for that, right? So earlier what happened is that because the kings and all wanted to know that when is it going to be full moon, for example, right? So, or they wanted to know when is there going to be no moon, because maybe that's the night they will attack and start a war, right?
Exactly.
You have an astronomer who's going to observe and tell you which night is the no moon night, right?
No moon night.
Correct. So that say the king is going to attack enemy on that night. So the advantage what happened is that because of that, a lot of almost all kings and queens always paid somebody to look up at the skies to tell them, phases of the moon, which planet is up, which planet is not observable, so that they can plan. And in that way, a lot of funding came for astronomy because of astrology.
Exactly.
Because otherwise, in normal times, who is going to pay you to look at the phases of the moon? Nobody is going to pay you for that, right?
Yes, ma'am.
Like, for example, I get paid by the government, but the government pays me to teach as well as do research. But otherwise, like say a person goes to a doctor when you're sick, right? The doctor has a function. But in that way, an astronomer, to convince people why do you need to do is, not very easy, right? And therefore, so that's what I was saying, that the advantage of astrology is that it gave a lot of funding for astronomy.
Yes, ma'am.
So the funding came. But the purpose what it was used for was obviously illogical, because I'm sure there were kings who started wars depending on what the astrologers said, and sometimes they won the war, sometimes they lost the war. So you know, and a lot
No,
of
India,
happy
all the people are running behind astrology, ma'am.
That's right.
That's why, invariably, madam, there is no, what can I say that everybody is going behind the astrology.
Yeah, but there's no
Some,
logic in it.
they,
And you don't want to,
they believe that mathematical calculations, they believe the persons. That's what I want to. You
I
gave
know,
very
but
good explanation.
the calculations are just to impress you, right? To impress
Yes.
the client, the customer, that see we are doing calculations. But how you apply it is also important, no?
Yeah, exactly.
Yeah.
Thank
So,
you.
that is the difference. Yes. Okay.
Thank you.
Yeah. Any other questions before I proceed? Are there any other questions?
Madam,
Okay, then I'll proceed.
sorry, madam,
Yeah.
there is a question in chat. Senthil Kumar has asked, how does the data science influence astronomical and astrophysical research?
Oh, it's very strongly. I'll come to that, but it's affecting it very, very strongly. Basically, because now in astronomy we have a lot of data. Earlier in astronomy we did not have so much of data. Now we have a lot of data, and therefore data science is being directly applied to astronomy. So, for example, I have two PhD students, and both of them, one is working on machine learning, and the other one is also working on neural networks, etc. Because now there's so much of data. And to understand it, we have to use the principles of data science. So it's being applied a lot. It is very much become part of what astronomers have to learn. Yeah. Okay. Sir. Any other questions? Or okay.
You proceed. Yeah.
Yeah. Okay, sir. So now let's come on to our next part. What do basically astronomers study, right? So I first showed you historically how astronomy is so linked to our lives, right? To what we are doing. Now let's see what do astronomers study. So one thing which astronomers study is, for example, the solar system. Now the solar system is our immediate neighborhood, right? What is right just in, which is right outside us. So we are here. You have the sun, you have Mercury, Venus, Earth, Mars, Jupiter, Saturn. And this is the solar system. So a lot of astronomers study the solar system, which is also very interesting to answer various questions. First of all, the most important question being, is there life in the solar system? Is there life on Mars, on Jupiter, on Saturn? What kind of lives? Venus was also, if you all remember, Venus was also considered a possible thing for life when we had the phosphine being detected on Venus. So a lot of astronomers spend a lot of time studying these things as well as their motions. Study their motions and how do they move, etc., and the stability of the solar system, etc. So now if you look up at some of you all who may be lucky enough to, when you look up in the night and you actually see the Milky Way, probably, I don't know, in Trichy maybe you all can see it, but in places like Hyderabad, we just can't see the Milky Way, no time of the year. Maybe you all can see it, but you see a patch of sky, in the sky, which is very bright. And if one actually looks through telescopes, you can actually see that this patch is made up of stars. And this is our Milky Way. There's been a jump over here. For some reason, stars have been missed out. But another study in astronomy is a lot about stars. I think that part has been lost, but we'll get back to it. So the Milky Way galaxy, the other thing is what we study is stars, individual stars. So if you look at these through telescopes, you will see individual stars. For individual stars, we can find out various parameters for them. We can find out their mass, their radius, their distance, and various other factors about stars. The other thing is we study galaxies. Galaxies are a large collection of stars, gas, and dust. If you have a reasonably good telescope, you can actually look and actually see these galaxies. And galaxies are of absolutely different sizes, shapes, colors, etc. And they're made up of billions of stars. They have typical masses of 10 power 9 to 10 power 12 times the mass of the sun. Now, if you look at the sun itself has a mass of 10 power 30 kilograms. By 30 kilograms, 10 power 30, you mean 1 followed by 30 zeros. Okay, that's the approximate mass of the sun. And galaxies, they are made up of billions of such stars, right? So it is 10 power 9 to 10 power 12 of stars, of suns, for example. So the mass of a galaxy could be 10 power 40, 42 kgs, right? It's going to be so heavy, it's made up of so many stars. It has a size In astronomy, we have a typical size defined, which is called light years. A light year is the distance traveled by light in 1 year. So to explain light years, if you actually talk about distances, right? For example, if I were to ask you how far is Hyderabad from Trichy, right? You would probably tell me, oh, in a flight it would take 1 hour, or in a train it will be overnight, right? So what happens is when we're talking about large distances, we change it to time, right? Instead of talking about what is the distance, you'll tell me how much time do I take to travel, right? To come to Trichy, for example. So instead in astronomy, that's exactly what we do, that since the distances are so large, what we do is we talk about the distances to travel. So for example, if the fastest thing we know to travel is light, right? And therefore, what we do is we actually talk about the distance which light will travel in a whole year. And that's what we call a light year, right? So we know that light travels 3 into 10 power 8 meters per second, okay? And we know that a year has 3 into 10 power 7 seconds. So if we multiply the two, you'll get 9 into 10 power 8 plus 7, which is 15. So you get 9 into 10 power 15 meters will be what you will travel in a year, right? That is the distance which light will travel in a year. But galaxies are so huge that from one end to the other end, if you have to travel, it would actually take 100,000 light years, okay? So that's the kind of distances we are talking about in astronomy when we are actually measuring or studying distance. Now we know that we are sitting inside a galaxy, which is called the Milky Way, and our galaxy looks something like this. We have a disk, like a dosa, it's flat. The central part is the bulge, which is little roundish. And if you look at it from top, you will actually see that it has what are called spiral arms. Okay, so these are spiral arms of the galaxy, right? And this is called the halo of the galaxy. So you have the disk, you have the bulge, and you have the halo. Now, Copernicus actually told us that the Earth is not the center of the universe. But further on, when we studied the galaxy using work of Shapley, we don't have time to talk about it today, but using work of Shapley, we know that the sun also is not in the center of the galaxy. The sun is 2/3 away from the center of the galaxy. So even the sun is not sitting at the center of the galaxy, right? So this is a galaxy which actually looks like us, but our galaxy looks something like this, and the sun is sitting somewhere outside, right? 2/3 away from the center, from the outer spiral arms. Now the galaxy also is not single, it's made up of a group of galaxies called the local group of galaxies, which the closest we have, the Milky Way has 2 satellites called the larger Magellanic Cloud and the small Magellanic Cloud. And then there's another galaxy which is called the Andromeda. And if you take a further view, you can actually see that these galaxies form kind of filaments, okay? So if you actually see, this is a survey which was called the 2-degree field survey. They just studied 2 degrees of the sky, and they actually saw that these galaxies form kind of filamentary structures in the universe, right? And using this, we actually can create a timeline of creation of the universe. So each of these things which I was talking about, there are people who spend their lives studying individual aspects of these things. Like I said, the solar system, the stars, the Milky Way, other galaxies, as well as studying the timeline of creation of the universe, which is cosmology. How did the universe build up, right? So now we'll come on to moving towards what is it that we have in India which can be used or for the study of astronomy. Now in India, we have a few observatories. This is an observatory called the Japal Rangapur Observatory, which is not very far from Hyderabad, 60 kilometers from Hyderabad. And this is a 48-inch telescope, which is run by Osmania University. You have this telescope, which is the Giravali telescope, which is run by Ayuka Pune. This place is quite close to Pune, about again 1 or 2 hours away from Pune. It is called the Giravali Observatory. This one is the Himalayan Chandra telescope, which is run by the Indian Institute of Astrophysics. It's a 2-meter telescope, which is in Ladakh. Here you see, this is the Mount Abu telescope, MIRO, which is an infrared observatory run by Physical Research Labs, Ahmedabad. And here what you can see is the Nanital Observatory, which is called Aries. Again, this is a 48-inch telescope, very similar to this one, the Japal Rangapur one. But now Aries has a new telescope, which is a 3.6 meter telescope. So this telescope has a diameter, the primary mirror has a diameter of 3.6 meters, and it has to be polished very accurately of the order of lambda, of the wavelength at which you're going to observe. So this is in Nainital, in a place called Devasthal, which is close to Nainital. This is another map of that 3.6 meter telescope. It's made up of, there's a dome, there's a slit, and you have the things over here. And there are various instruments on the telescope. There's a faint object spectrograph camera, there's a near infrared spectrograph, there's a high resolution optical spectrograph, and there's an integral field unit, which is all there at the 3.6 meter telescope at Devasthal. Other than that, the pride of the country is the giant meter radio telescope. We have a telescope which is called the GMRT. This is made up of 30 antennas. Okay, there are 30 antennas. Each of these antenna actually has a which is actually 48 meters across. Okay, it's 48 meters across, and this has been totally indigenously done in India by Professor Govind Swaroop, who actually designed this telescope, and with a certain design called the smart antenna design. And this is a world-class facility which we have. Like I said, it's made up of 30 dishes which form a Y kind of a shape. And what it actually does is it synthesizes an aperture as though it was as big as this, right? So though you have smaller dishes of 45 meters, but they are put along this thing. So there's a technique in radio astronomy called aperture synthesis, which is used to actually, synthesize a larger dish size. So it gives you very good resolution because it's actually doing it in this. And it also works in low frequencies, which is another very important thing about the GMRT. There's another telescope we have in India, which is called the Opi Radio Telescope. And it's a very interesting telescope because if you can see, this is a radio telescope, so it's made up of parallel. So radio telescopes look like this. They are basically made up of antennae. It operates at the frequency of 326 megahertz. And what is done, what was very interesting, is that that sources rise and set. So what they did is in OT, they found this slope, which was a north-south slope. And they placed this thing along the north-south slope. So now these dishes just have to steer in only one direction. So if they're supposing observing an object which is over here, as that object rises and sets, you just have to have this telescope moving on one axis. Otherwise, you will need the telescope to move on two axes. But in this case, because the slope itself is north-south, everything else will rise from east, set, and west, and you can just move these antenna to track the source in this way, right? So this is also a part of the NCRA, the National Center for Radio Astrophysics, which also runs GMRT, and that's the Ooty Radio Telescope. In the future, what is being planned is what is called the TMT. The TMT is the 30-meter telescope. So it's a telescope which is supposed to have a primary mirror of 30 meters. It's made up of 492 segments, each of 1.45 meters. And this is a thing which is being planned in Hawaii, in which a whole bunch of countries are contributing, which includes the US, essentially Caltech, University of California. There's Canada, Japan, China, and India. So these are essentially the 5 contributing countries which are contributing in the building of TMT. And India actually has a 10% contribution in TMT. And we are actually building parts also of the telescope, as well as even the software development for running the telescope is basically being designed by Indian software programmers, etc. They are doing the TMT. The other important thing that India is part of is called the SKA. I'm sorry, I forgot to mention that most of these telescopes are very, very expensive projects. And therefore, what is being done is not one country, but a set of countries contribute to the building of the telescope. So in radio, there's a telescope which is called the Square Kilometer Array. And this is actually being built across different continents, okay, in South Africa, in Australia, etc. And in this, a whole set of countries are, so basically Australia, South Africa is where the telescopes will be. And a whole set of countries are contributing into it. Australia, Canada, China, Germany, India, Italy, New Zealand, South Africa, Sweden, Netherlands, United Kingdom. So these are the contributing countries, and this is a real the spectrometer array is going to be a real phenomenal radio telescope, because if you actually see it, it's really something which is this thing. Now in India, what we have is we have the Astronomical Society of India, which coordinates the efforts of all astronomers in the country. And it was established in 1972. It has not 1,000 members, maybe it's more. Maybe active members, maybe about 1,000. And what the Astronomical Society of India does is we have meetings every year, and they have a bulletin, and they do various activities for popularization of astronomy, etc. And I'd like to slightly talk about even the Indian space program, because that's also very related to astronomy. And a lot of students may be interested in careers essentially in the space program, which would mean being part of ISRO. Now, the Indian space program is a very prestigious, commendable program which we have. The picture that you can see over here is of the Polar Satellite Launch Vehicle, right? We have the geosynchronous, the GSLV, and the PSLV. And this is the launch of Mangalyaan, which you can see over here. And ISRO, you can see, is that India developed its space program so that it could end its dependency on foreign service. It can actually, it launches its own satellites, as well as it launches satellites for a whole bunch of countries, right? And it's a very active space program. We had the Chandrayaan, we had the Mangalyaan. So the Mangalyaan Project was something that the country was very proud of. It was the Mangalyaan Mission, where we actually launched a thing to Mars. And what was interesting is that if you compare the launch vehicle which we have, the Americans have much more powerful launch vehicles, so they could launch directly to Mars. They had the Maven mission. But India, we do not have such a powerful launch vehicle. And therefore, we applied another, a slingshot kind of technology to go to Mars. So if you've done with slingshots, you have a stone with a string, and you move it around. So that's exactly what they did, is you had the launch taking place, and the satellite took various orbits, 6 orbits, in which it finally then moved on to Mars. So that's how the Mangalyaan mission was done. So you actually saw it was a beautiful exhibition of technology, of how could you actually launch to Mars. And like I said, it is the mother of all slingshots, where they actually did it at very minimum amount of fuel and with very minimum kind of expenditure. So the importance of the Mangalyaan mission was that it was the first ever country to succeed in the Mars mission. And you had USA, Russia, European Space Agency. They succeeded only after repeated attempts, but India managed in the first attempt itself. So it's now the 4th nation, or the group of nations, because ESA is actually a group of nations, to actually have launched to Mars. So like I also mentioned, is our launch vehicle is not as powerful as the American one. So the American mission, when it was done, it obviously costed lots more money, $671 million, while ours was much cheaper, because our launch vehicle is not that powerful, not so, doesn't take that much of money, but we actually could do it. The other important thing which India is doing in astronomy is AstroSat. We have a dedicated satellite which is just meant for astronomy. So this satellite actually has telescopes. It has an ultraviolet telescope called the UVIT, and it has 3 X-ray telescopes. One is called the CZT, the SXT, and the LAX-PC. All these 3 are X-ray telescopes which are on AstroSat. And this is the scanning sky monitor, which is an optical. So that the satellite was dedicated to astronomy, just for astronomical observations. And it is very much operational, and you can still observe with it. It is the first multi-mission mission which was done. It observes, like I said, in X-ray, in optical, in ultraviolet, and all the payloads are operational. It is still very much in use. It has all these instruments, as well as these are the specifications for it. So that's the launch of AstroSat, and more details. We don't have too much of time, so I am not going to go into details about it. But what is important about it is that the instruments, etc., they were all developed over here in India with some for collaborations, and they are all very functional and being used. So we'll go into that. The Chandrayaan-2 mission was launched, and some of you all would be aware of it. It had a orbiter, the lander. The lander had some problems, but these are just what you call, stepping stones to the space program. So part of the failures, failures are part of the deal. So Chandrayaan-2 is also being planned, and Chandrayaan-3, the next one, and hopefully that should work out. There are various plans which we have in the future. The Indian space program is Chandrayaan-3, which is a repeat of Chandrayaan-2 with the lander, rover, etc. There is Gaganyaan, the idea of sending humans out in space. There is the Lunar Polar Exploration Mission, which is being planned for 2024 with JAXA, with the Japanese. There is the Aditya L1, which is a satellite which will basically observe the sun. And this is, very soon going to be launched this year or next year. And there is Mangalyaan-2, Shukrayaan. So there are various plans which the Indian Space Organization has. And obviously, they do need young minds to participate in their activities and add on to what they are doing. So that's Aditya L1, I was talking about, Mangalyaan-2, Gaganyaan, which I told you about. And therefore, what you see is that astronomy in India, I tried to give you an exhibition or a thing of what are the different sources in which you can actually, contribute. It could be in the study of astronomy itself, or it could be even in the space program. And the space program, like I said, has a lot of plans for the, immediate future, where young minds and young students can contribute and build up careers in research, in teaching, as well as in the space program. And so astronomy requires a good understanding of physics, maths, computers, chemistry, various other subjects which are very important in the understanding of astronomy. And now just another 5 minutes, sorry, I've taken a lot of time, is that there are various ways of approaching it. So there are various mathematics departments in the country which actually study more the motion of planets. So these are there in ISM Dhanbad, in Muzaffarpur, at Maulana Azad University also, in University of Delhi also, in Jamia Millia also. So there are groups which work on celestial mechanics or the movement of heavenly bodies. Okay, from the mathematical point of view, you could study it from that way. The other way is to do it from the astrophysics point of view. So there are various physics departments in the country. For example, Osmania University is the only university in the country which actually has an astronomy department. There's an MSc in astronomy, MSc in astrophysics. Other universities, there are many more which have papers in astronomy and astrophysics, which include Mumbai University, Delhi University, Pune University, Lucknow University, as well as many of the other places which have integrated master's programs. For example, the ICERs, IST, University of Hyderabad, and various other ways. So one of the other ways would be just to do a master's in physics, right? Which you can do it in any of the universities or even in the IITs, or like I mentioned, ICERs, IST, etc., and then join for PhD programs. PhD programs can be done in various universities in India. Some of them are Punjabi University, Patiala, Osmania University, Aligarh Muslim University, in Bangalore, in Delhi. And then there are a whole set of institutions in the country. For example, the Harish Chandra Research Institute, the Indian Institute of Astrophysics in Bangalore, Institute of Physics in Bhubaneswar, the Inter-University Center for Astronomy Astrophysics, Ayuka in Pune, TIFR, Tata Institute of Fundamental Research in Bombay, National Center for Radio Astrophysics, which is in Pune, NCRA. Then there is the Physical Research Labs in Ahmedabad, Raman Research Institute in Bangalore, SN Bose Center in Calcutta, Institute of Math Sciences in Chennai, and a whole set of other institutions where you can actually go in for a PhD program in astronomy. And so I will finally end with that, stating that exploration is in our nature. We began as wanderers and we are wanderers still. And we've lingered long enough on the shores of the cosmic ocean. We are ready at last to set sail for the stars. These are words of Carl Sagan. And with that, I would like to bring to your notice that astronomy has reached a very, a very interesting stage where now there is so much happening in astronomy in terms of data, in terms of telescopes, in terms of observations, space programs, the JWST, the James Webb Telescope. There's so much happening that there are lots of careers and pathways that you can actually think of. So thank you. I'll end with this, and I'd be happy to answer any questions.
Thank you, madam.
Thank
Thank
you,
you
madam,
so much
for your nice presentation.
Ma'am,
Okay,
Yes,
sir.
sir.
I have two questions. Since you elaborated so many research institutes now, the graduates required only that, ma'am, job is concerned, ma'am. There is a scope for astrophysics, madam. Because
Sir,
today
just a minute.
students.
Sir, just a minute, please.
No, can you hear me, ma'am?
There's a lot of echo happening.
Yes, sir.
S-
Yes, audible.
Yes.
Ma'am,
Sir, just a minute, sir.
is it audible, ma'am?
Sekdav,
Yes, sir. I understood your question. You're asking about job opportunities, right?
Sekdav, sir, நீங்க கொஞ்சம் மியூட் பண்ணிக்கிறீங்களா சார்? Can you please mute, sir? Yeah. Sir, can you please ask again, Balaji, sir?
Sir, good afternoon, sir. I need to ask one question from madam.
Yeah.
Actually, two
Yes.
questions, sorry. The first question is, what about job opportunities, ma'am?
Yes, sir.
Because when I meet to students, I have to encourage them to go for this course where they can employ them. That's the problem nowadays. Because everybody is going for engineering and other areas. The scope
Yes, sir.
towards this astrophysics is very, very little. Because men are aware these all those institutions, ma'am. That's what I want to ask this question.
Yes, sir.
And
Yes, sir. So,
second
yeah,
question
thank
also
you.
I put to ma'am.
Yes, sir.
Bit about aliens, ma'am, because the talk is going on, so much of alien story is coming. If it's possible, 2 minutes at least you can say, because you are scientist, no, madam, you can say what is actually true.
Okay, sir. Okay.
Thank you.
sir. Okay.
Thank you.
Okay. So the first questions are about job opportunities. So I will not tell people that getting jobs in astronomy is as easy as with engineering, right? But even in today's time, even with engineering, there are lots of engineers also who are unemployed, right? So that it's not even that engineering is the solution. But if you see all these institutions which I've mentioned where you can do master's program or PhD programs, obviously all these institutions need faculty, right? They need people who can teach at MSc, teach at PhD level, all these places. So these are all the places where you will have job opportunities, right? In the sense of being either doing teaching or doing research in any of these places. Right. Other than that, even for example, the planetaria are there. You have a lot of planetariums in the country, and in the planetarium also they need to employ astronomers, and do it like that. So essentially, it is and most of these places, what happens is the PhD you will get will be a PhD in physics. For example, if you do a PhD with me, you will actually end up getting a PhD in physics, and with that PhD in physics, you can apply to any physics department in the country, right? So that includes all universities, all colleges, all these institutes. In all these places, you can get jobs because, like I said, your PhD will be in physics. So wherever there's a physics department, you can get a job as faculty member in any of these places. So you could be teaching or you could be research in any of these places. So that is for job opportunities. So there are plenty of job opportunities. Every place has a physics department, right? All universities, all colleges have physics departments, and in physics department they definitely need teachers, right? They need people who will teach, and all these people can teach. So like what I also do is I teach more physics, though my research is more in astronomy. So my PhD students, the research they do is in astronomy, but the teaching which I do, most of the time I teach more of physics. I teach less of astronomy and I teach more of physics. So, like I said, in jobs in all physics departments all over the country. The second question, sir, you were asking about was about aliens, right? So, when I showed you the picture of our universe, right? I showed you that the sun is just one star in our galaxy, and in our galaxy we have billions of stars, right? And then in the universe there are billions of galaxies, right? That's not the only galaxy; there are billions of galaxies, and therefore what you see is that definitely there are so many stars in the universe, so many galaxies in the universe. So many of these stars will have planets, right? And why should we not think that some of these planets could have conditions which are good for life, right? So there's a very famous statement made by Carl Sagan that the universe is an awfully big place, right? And if it was just made for us, it seems an awful waste of space, right? It can't be that the universe was made so big just for us, right? You have so many more planets, so many more stars, so many more galaxies. And if you want to believe that only the Earth was made for life and the rest of the universe is, just for us to look at, that's obviously something which is not very convincing, right? And therefore, chances that life is there on these other planets, right, which are there, is very possible. And therefore, now what we are actually looking for is what is called extrasolar planets. Extrasolar planets are planets which do not belong to our solar system, but they belong to other stars, to other solar systems. And we already know more than 4,000 extrasolar planets, okay, which we are observing using various telescopes and various methods. We actually observe and look at extrasolar planets. So now the first thing is detecting extrasolar planets. How do you detect them? The second thing is then actually trying to study them. That is to study their atmospheres so that you know whether their atmospheres are good for life. Can life survive on those atmospheres? So studying extrasolar planets. So for example, James Webb Space Telescope will also look, we already have a list of extrasolar planets, right, which are interesting, which could be potential places for life. So now, for example, James Webb Telescope will also observe some of those telescopes to actually see whether do those planets have atmospheres which could be capable of life, or looking for what are called biomarkers. Biomarkers are indicators of life. So in what way can you have biomarkers or indicators of life on other planets? So at present, astronomy is at a stage where we are actually searching for aliens. We are actually searching. So at present, the searches, we have found, like I said, more than 4,000 extrasolar planets. Now we need to study their atmospheres and look for indicators of life. So it is the process. We are searching for it, but we haven't yet found it. We are searching.
Is there any student orientation program, ma'am? Can you send our students to the place is there such activities there now?
Can we send students to where?
To that orientation, some kind of mini project or something else that they can do their research in astrophysics. Because nowadays we are sending students towards some university to do some research in crystal area or electronics, something else. But as far as astronomy is concerned, students are very, very minimum they show interest,
Yes, sir.
Is there any student over?
Yes, sir. So I have a lot of students doing projects on my YouTube channel. Also, we have a lot of details on projects.
Yes, ma'am. That's what I need, ma'am.
Yeah. Also, there is a session specifically on projects only, which is being done. There are many projects students can do. So first of all, there are citizen science projects in which you don't need to even know much of science. With little bit of understanding, you can actually do that. So there are many citizen science projects in which you can actually look for asteroids. If you find an asteroid, it can get named by you. You can actually look for planet hunters. You can actually look for galaxy morphology. There's Galaxy Zoo. There are many, many citizen science projects which are meant for people who don't have science background. If students have science background, then again, there are many, many projects which students can do, basically because there is a lot of astronomy data available, okay, which is called astronomy archival data. So there's a lot of astronomy data which is available on the internet, and this is freely available for everyone. So what happens is you can actually access that data and do projects using that data. So actually, especially in this COVID things over here, and get in touch with me if you are interested in anything. Okay, so.
Sure, thank you, sir. Thank you, sir.
Yes, sir. I'm sorry to be doing self-promotion, showing you my own YouTube channel, but that's the easiest for me to guide you to, because those are the ones that I've done. Then there are many more resources on the net, and you can have a look at that, not just mine.
Sure.
But I hope I think I was sharing.
No, it was fantastic. Fantastic. Thank you.
Yes. Finally, you have a question, right?
I wanted to ask if you have any
can't, it's not, for some reason it's not showing this, but you could just send me email and I will this thing, but you can go to our website and you will see that there's self-finance PhD program which they're now advertising for. So even part-timers can also attend it or whatever. And there are 2 positions for me. So you can email me also if you want for more details. Right?
Thank you, ma'am.
Yes.
Ma'am, good afternoon. This is Nilufar.
Yes.
Ma'am, is it possible to have a online astronomical show to the students, ma'am?
Yes, we can. We can do it with, there is a software called Stellarium. Okay.
Okay.
What Stellarium does is it simulates the sky. Okay. So it will, on the computer screen, you will see the sunrise and the sunset and the stars move, etc. Right. So we actually did it also recently for some nurture camp for students, wherever you want on whatever date. Right. So you can do that with Stellarium. Yeah. So it can be done in the sense we can show students the simulated sky, not the real sky, but the simulated.
Ma'am, that simulation is based on the software programming or on the parameters that we give at the time we need to watch it?
No. So 1 minute, I'll just try to show you.
Yes, ma'am.
So maybe I can show you. 1 minute. I hope you all can see my browser. Yeah?
Yes, ma'am. Yes.
So what happens is, this is Stellarium. So what Stellarium will do is it will actually show you for a certain place, it will show you what does the sky look like. Oh God, this is for the, but see, so for example, it will show me the sky. If I'm sitting over here, this is the south part, this is the sky, this is the position of Vega, of Deneb, these stars, where are they, how will they move, etc. Right? So
Yes.
you can actually see this. It will actually simulate a sky. So for example, if you do it in the day, it will show you this is the place, here is the sun, right? And then I can show how this place will look like in the evening, say at 8 o'clock. You will see these stars overhead, right? And these are the stars you will see. Here is Jupiter, here is this, here is that, right? So in that way, we can show them what the sky will look like, say from the west, from the east, from the south, and how does it change through the night, right? You can draw the constellation, show them the constellation patterns, right? And what will that look like? And like here, you can see over here, it will actually draw these constellations. Yeah, sorry, these advertisements are coming. But you can draw the constellation, show it to them. And the good part about Stellarium is that after session gets over also, the students can install the software on their phone or their laptop. So later on, when they, go back home, right? That's what we tell them, that install the software on your phone or your laptop or whatever. And then when you look up at the sky, you can actually see the same stuff, right? So it will, it is a good initiation process, They can start off by learning Stellarium, right? And after that, the child just needs to go out with his phone and look up at the sky. And they will start identifying constellations and everything, right? And gradually they can become experts at it, because every day they have to just look up, have their phone. The phone will help them to, from east side, what are you seeing? Suppose they're looking at some bright star, they don't know what that is. They can use the software to say, okay, that is Jupiter that you're seeing, or, whatever you're seeing. And in that way, they can, practice and learn. So for many students, we are actually doing it. Yeah, so someone has shared, so I can, so what you can actually do is, you can actually, okay. So the people who want to apply, you'll just send me mail and I can this thing.
Sure,
Yeah,
ma'am.
so-
Sure.
Yeah, somebody else has also
Ma'am,
mentioned about
please.
Rad at Home. So Rad at Home is also run by a friend of mine called Anand Hota, and he's also been doing that. And essentially, in Rad at Home, there are a lot of BTech students, right, who are unhappy engineers who would like to do astronomy, and Anand helps them in teaching them some amount of astronomy skills. Yeah, so Rad at Home is also a very good initiative which helps to initiate students into astronomy. Yeah. So you can
Thank
participate
you, ma'am.
in Rad at Home workshops. Anand conducts workshops at regular intervals, which you can attend.
Thank you so much for your information, ma'am.
Welcome, ma'am.
And some of our students were they are joining in the somewhat like watching the telescope using astronomical datas and how
Yes.
to catch the. Is it the real data, ma'am?
From where are they getting that data?
No, ma'am. They are asking to install the same thing like this type of software, and they are
Yes.
asking to catch it on day by day during that complete course. But
Yes.
our students is not getting an option to do so. So, is there any other easy method to study on these?
Yeah, so stellarium is just simulating a star, right? So those are not real observations. The other way of getting observations is there is something called LCO, Large Cumbres Observatory. These are robotic telescopes all over the world. So we are global sky partners for them. So in their case, we can observe using their telescopes, which are placed all over the world, and they can contact me and get data from those telescopes if you want. Otherwise, to get telescope data, you have to write a proposal, and the proposal has to get accepted. Then you will get data. But if you want data
Okay.
like what I'm talking about with this Las Cumbres Observatory, those are robotic telescopes. I have telescope time on that, so I can get any data that they want.
Okay, ma'am. Thank you so much, ma'am. I will mail to you, ma'am. Sure.
Yes, yes.
Thank you.
Kumara Asifa is asking, can you help me on the study of stellar structure and evolution in tele-parallel gravity theory? I don't know what is tele-parallel gravity theory. Asifa, I don't know what is tele-parallel gravity theory. So stellar structure and evolution is my specialization, but tele-parallel gravity, I'm sorry, I don't know. It says it's also-
Okay, it is part of modified gravity.
Okay. No, I'm sorry, I don't know that very well. Stellar structural evolution, I know. That's my subject, but I don't know tele-parallel. Sorry.
Okay, so which part you can help me?
I know stellar structure and evolution. Stellar structure and evolution, yes, I can help you. But the tele-parallel gravity theory, I do not know. I know the normal
So-
gravity theory, but I don't know.
Okay, I need your help on this part. On
That I
stellar
can help you.
structure.
Can make.
Okay, I will mail you.
Okay, sir. Okay.
Thank you.
Well. Shrikant Bandari, yes, there are many projects for MSc students. Yeah.
Okay, ma'am. Thank you very much. So, if there is any questions in the YouTube also, people you can ask.
Yes. Surinder, okay, it's on YouTube also.
Yes, madam.
Just
Yeah,
share the.
yeah. I will share the link, ma'am.
Okay, sir. Oh, thanks. I think there are no more questions. The last one was Karthik on MSc projects, but that's a very long answer. But yes, there are projects for MSc students. Many.
Okay. So, thank you, madam. If there is no more questions, we may move to vote of thanks. Sekdav, sir.
Dear participants, we are coming to the conclusion part of the first day of our faculty development program. We had a nice session on career pathways to astronomy education and research by Dr. Priya Hassan, Assistant Professor, Department of Physics, Maulana Azad, National Urdu University, Hyderabad. She is the co-chair of the working group of women in astronomy in the International Astronomical Union. On behalf of PG and Research Department of Physics of Jamal Muhammad College as well as Sigru Collab, Bengaluru, I am happy to thank our resource person for our informative and interesting lecture. It was very much encouraging. Her session was very much interesting one to all the participants, starting from the state of astronomical studies and India's contribution towards it, the facilities established in India for pursuing studies on astronomy, as well as various avenues openings available to the research scholars. She patiently gave information about all these things. So on behalf of all the participants as well as the organizers, I thank you, ma'am, for your interesting lecture. I thank all the participants also for their patient hearing and their interest they have shown towards this. The participants raised many pertinent questions to which our resource person gave satisfactory and convincing replies. So on behalf of all those present here, I would like to thank our resource person for this second session. Thank you. Dear participants, tomorrow's program, thank you, ma'am, welcome. Tomorrow's program will start by 9:30 a.m. We will be having 3 sessions. The first one will be on decentralizing astronomical education by Dr. T.B. Dinesh, Director, Serolach, Bengaluru. The second session will start by 10:30 by Mr. Ramesh Session. His topic will be on astronomical data and technology. He is the head research and development cell, Sigru Collab, Bengaluru. His talk will end by 12:30 p.m. The third and concluding session will be on astronomy for development, delivered by Mr. Ramasamy Venugopal. He is the head operations, Office of Astronomy for Development, International Astronomical Unit. So with this information, I would like to conclude this first day's program of faculty online development for astronomy education. Thank you, participants, for staying with us. Thank you, resource person, and all those who are associated with. We'll meet tomorrow morning by 9:30.